My name is Drazen Petrov and I work at BOKU Vienna, where we use computational tools to study soil organic matter. In this presentation, I would like to show you a few research highlights from our group. I would like to start with a short introduction to soil organic matter, which is one of the key components of soil as it plays an important role in a range of processes, including environmental fate of pollutants, nutrient availability, soil degradation, and so on. While we know a lot about soil organic matter at a macroscopic level, our understanding at the molecular microscopic level is very, very limited. In particular, exact chemical composition, the 3D structures of these molecules, how they're combined together, how they interact together, it's all unknown. Yet this all affects the behavior of soil organic matter and therefore also affects these processes. Addressing this is the main research goal of our group, or more precisely, we are trying to better understand soil organic matter at the molecular level and relate this to macroscopic properties. At the core of our research is Vienna Soil Organic Matter Modeler, which is an automated tool for generating SOM models. It takes as an input various parameters, including elemental composition, organic composition, water content, and so on. And then also based on a database of fragments, it puts everything together such that we get a 3D model that corresponds to these input parameters. Vienna Soil Organic Matter Modeler, it's available online, and this tool will be presented in more details on Tuesday morning in this session. To study behavior of created models, we use molecular dynamic simulations, which is a modeling method that provides insight into interactions and motions at the molecular level. In a way, this is a computational microscope. Here I'm showing a video of leonardite interacting with mineral surface. If you're interested in this line of research in our group, then please visit poster presentation of Edgar Galicia, a colleague from the group. Let's now look at some application examples of this methodology. Here we are looking at the effect of compactness on behavior of leonardite, one of the samples of soil organic matter. So we created different models of the same composition of leonardite at different level of compactness. And then we also add a different amount of water to these different models. And then we use molecular dynamic simulations to calculate different properties. Here I'm showing density, and it's not surprising that the compact model has higher density than the less compact one. However, this is more pronounced at the low water content. When it comes to interaction energy, the compact model shows much lower interaction energy, which means that the aggregates and supramolecular structures that are formed in the compact model, it's much more tightly bound and more stable. When it comes to dielectric screening, these two models are more or less the same. In this second example, we are looking at sorption properties of the same system, leonardite. And this we did using non-equilibrium free energy calculations when we are growing and removing small molecule in leonardite system and in vacuum. And then when we repeat this hundreds and hundreds of times, then we get distributions of work of growing and removing, which then in the end can be translated into free energy absorption. More importantly, this we can relate or compare directly to the experimentally measured sorption free energy. And when we do this for 16 small organic compounds, we get very nice correlation. On top of this, we actually looked also at different microscopic properties and how they relate to the calculated sorption free energies. And then, for instance, in this case, when we are looking at hydrogen bonding pattern, we obtain very good correlation between hydrogen bonding pattern and sorption free energy in leonardite. And that also holds for some other properties as well. In this example, to take advantage of versatility of Vienna Soil Organic Matter Modeler, we turned our attention to different samples of soil organic matter to study what is the effect of different composition on properties of the system. First, we just looked in 15 systems that we modeled how they compare in terms of composition. So on the diagonal, where we actually have exactly the same systems, this is very dark color, and then the more lighter colors show that two systems are much more different. And then we also used this heat map to do clustering in terms of composition for these 15 systems. On top of this, we did principal component analysis to see where the differences are coming from in composition. And what this analysis shows is that aromaticity and acidity, or in a way the carboxyl content, are the two major properties that describe the differences in the composition. And then we simulated these 15 systems and then also calculated a range of properties from these simulations. And then we are trying to relate these calculated properties with the composition, or more precisely with these two principal components that come from principal component analysis. When a trend in these properties compared to the composition are correlated, then we are showing a thick line here. And then if there is no correlation, then we plot a thin line. So this analysis shows is that the second principal component analysis, principal component is much more important, and then that's the one that determines the changes in the properties of, or like the behavior of these systems, which is the amount of carboxylic groups within the system. This brings me to the conclusions. So using Vienna soil organic matter modeler that is available online, we can generate representative models of realistic soil organic matter samples. And then we can use these models to study the behavior of such systems and also calculate various properties, including sorption-free energies. Finally, I would like to thank Jerko Escalona, who was a PhD student in our group, who did most of this work that I presented today. Chris Ostenbrink and Martin Gertzabek, who are the heads of the modeling and soil groups at BOKU, the whole soil modeling team, FWF for financial support, and you for your attention.